Hi class. Today I want to talk about the photoelectric effect. So this is an important effect that uh, that led Einstein to suggest that light is not does not always act like a wave, but light acts like a particle. And he actually won the Nobel Prize for his work on the photoelectric effect. Einstein did a lot of interesting work, but the one thing that he won a Nobel Prize for was his work on the photoelectric effect. So the first thing I want you to think about is just a wave. Here we see a water wave being generated by a disturbance. And we see that the amplitude of the wave is high, close to the source of the wave, and the amplitude of the wave gets smaller as the wave moves away from the source. And imagine that this water wave ends up hitting a beach over here. Pretend there's a beach over here, and on that beach you've got a bunch of little rubber ducks sitting on the beach. And you might say, well, if the amplitude of the wave is small, the rubber ducks would not be disturbed. But if you make the amplitude of the wave bigger, if you make a larger disturbance here, and the amplitude of the wave is large enough, it would knock these little rubber ducks that are sitting over here, it would knock them over. It would push them around. And you'd probably also say that it really doesn't matter what the frequency of the wave is. Here we have a little picture of a low frequency wave, and here this would represent a higher frequency wave. The peaks of the wave are closer together. Um, and you'd probably say it doesn't really matter so much about the frequency of the wave, whether or not it's going to knock over these rubber ducks. You'd probably say it matters more so about the amplitude of the wave, the height of the wave, whether these rubber ducks are going to get knocked over. And you would be right. But now let's look at the photoelectric effect and see why that changed things a little bit. So here, the photoelectric effect is an effect that is observed when you shine light onto a metal plate. Electrons are ejected or come off of the metal plate, and we can sense that as a current. So here we have electrons flowing from one plate to another, and as we know, a flow of electrons is current, and we can measure that on a amp meter. So this effect was observed back in the late 1800s, and nobody really knew how to explain it and what to make of it. But certain things made sense. One thing would be if you make the intensity of the light larger, you get more electrons being ejected from the surface. So here with a greater intensity of light, we get more electrons coming off the surface. But with a lower intensity of light, we're going to see less electrons coming off the surface, fewer electrons. And we said, well, that makes sense because the intensity of light is kind of like the amplitude of the wave. You could think of the intensity of the light as the amplitude of the wave. And so with a larger amplitude wave, we're going to disturb and eject more electrons, much like if we had a larger amplitude wave, we would knock over more rubber ducks on the shore of our pond. And so this aspect of the photoelectric effect made sense. What did not make sense was that if you changed the light, so if I made a lower frequency light, here for example a red light, no matter how intense I made the light, it would not eject any electrons off of the surface. So that was kind of surprising. And the other thing that was very surprising was that if we made if we chose uh, a, a frequency of light that did eject electrons, so for example, in this case, this color of light is ejecting electrons, but if I made it less intense, if I made it more dim, you would say that's a lower amplitude wave, and so we probably shouldn't see uh, electrons being ejected from the surface, at least at some point, right? So here we have less intense light, and we see less electrons coming out. But if we knock it down to very, very dim light, yes, we do see less electrons coming out, but we still see some electrons coming out. They come out somewhat infrequently, but you do still see some electrons coming out. And this result in particular was a somewhat confusing result, because people said if light behaves like a wave, this very, very dim light, granted it's at a somewhat higher frequency, but this very, very dim light is kind of equivalent to a very, very shallow, very, very low amplitude water wave. And we would think a very, very low amplitude water wave would not knock over any rubber ducks. And the photoelectric effect, the thinking was analogous to that this very, very dim light should not knock off any electrons whatsoever. And so they couldn't really explain this. And what Einstein did was he thought about it and he analyzed the experiment. And his conclusion was that light does not completely behave like a wave, because a wave is going to get the energy in a wave gets more spread out as you get further and further away from the source. And Einstein said, light doesn't actually behave that way. You want to think of light as almost like marbles rolling across a floor. So when a wave is created, these little marbles shoot out in all directions. And these little marbles can carry the energy of the wave. But because they're little marbles, they're like particles, the individual particles will never lose the amount of energy that they have. The energy in each individual marble will not spread out and thin out. Even though the marbles, as you get further and further away, might separate themselves from each other, the energy in the individual packet will not thin out. And so what he said was, light behaves this way. Light behaves like little wave packets of energy. And he called these packets photons. And to explain the photoelectric effect, what he said was photons of low frequency light, like red light, it doesn't matter how many of these photons you shine on the surface, they just do not have enough energy. Each individual photon doesn't have enough energy. Each individual red marble, you could think of them as the red marbles or smaller marbles. They all travel at the speed of light, but you can think of the red marbles as smaller marbles, and they just don't have the energy to kick off any electrons. The blue marbles are higher energy marbles. You could think of them as perhaps being physically larger marbles. And when they hit the surface, they do have enough energy to knock off electrons. So it would be equivalent to, instead of thinking as light as a wave which gets continuously less and less energetic as it moves outward, if you thought of it as little discrete marbles, and if we send in a bunch of blue marbles, we'll be able to knock over our little rubber ducks, because these blue marbles are big enough, they have enough energy to do things, to dislodge things. And that's why when you send in blue marbles, whether you send in a whole bunch or just a few, they will still knock over the rubber ducks, or they will still dislodge electrons from the surface. And so Einstein's conclusion was that light does not behave like a wave that continuously thins out. Light behaves like a bunch of wave packets, but these little wave packets do not thin out. The energy in these wave packets stays together, much like a marble stays together. Even though it moves outward, the energy in this marble would stay together. So he explained light as, yes, it behaves like a wave, but it behaves like a wave packet, and this little wave packet behaves like a particle. It does not spread out. It does not thin out the further it gets away. It stays together as a small particle of energy, a particle. So, and he called those particles photons. And so Einstein changed the way we think about light and all electromagnetic radiation. The same would be true for radio waves and X-rays and microwaves and so forth. All electromagnetic waves behave like both a wave and a particle. And that was the important conclusion from the photoelectric effect. So I'll send you guys a video or two and a short quiz on the photoelectric effect. Thank you.